Howdy ho, how's it going? So today we are going to try out the DETR, the end-to-end object detection with transformers from Facebook AI Research. And they have a GitHub repo, and they pretty much give you everything, like the model, the pre-trained weights, and so on. So today we're going to check out how easy it is to get started with that. So in order to do that, they have like a collab, but we won't look at it too much. I've glanced at it. We'll basically see how far can we go without looking at it too much, and how easy is that. So what I've done is I've spun up a collab that I will share at the end, and I've imported Torch and just loaded the model so you don't have to wait for that to happen. So I've loaded that up, and now we have it in the cache. So now we can basically go ahead and load an image into the model and try to detect objects in the image. So first of all, this is super easy, right? You simply load this from TorchHub. It's kind of like the TensorFlow hub. You simply give the name of the model. You say, I want it pre-trained, please. Shalaga boom, you now have a model. So if we look at that model, this is going to be this entire DETR model right here with all the transformer and ResNet and whatnot. Okay, this is almost a bit too much right here. So what we want is an image. So let's go find an image. Where better they find an image than Google? So let's find an image of dogs, because dogs is one of the classes in this Coco dataset. This one's nice, right? Okay, so we want the image address. We want to load it in here somehow. So so that the URL is, let's make this into some sort of like an input thing where we can paste the URL right here. Okay, there we go. So we have this right here, and that's the URL. All right, no, that's not the URL at all. Is it? Bada bim, bada boom, bada bum. Cool, better. Now we need to load this. For that, we're gonna use the requests library. Always a pleasure. Requests. So the way to load a binary file is you can put the URL here, and you can say streamed here. I glanced this from the other thing, and the raw entry will get you the eventual the bytes. No? Oh, sorry. Get URL stream. Yeah, so this will get you the sort of the bytes of the image, and then you just say image.open, and of course we need the image from the PIL library, the Python image library. So import image. We got that, and we can open that image up, and with a bit of luck, yeah. So this model expects, I think Coco dataset is 640 by 480 images, but they, if you can see right here, and we're going to take a quick glance at their transforming, they resize it to 800. So we're gonna steal that part right here. People last time were some found it really funny that I called copy pasting to go Siraj. So from now on we'll call it just Sirajing. What we also need are the class labels, because that's defined in the Coco dataset, right? So these are the class labels. Let's take those, and okay. So this T here, these are torch vision transforms. We're gonna need that. So from, let's say, so if you don't know torch vision, it's kind of an addition to PyTorch that just helps you with images, and has a lot of data sets, and these transforms, they're really helpful because, so let's call this image, because you can, you know, resize, but they have much more like random cropping and rotating images and so on. Pretty much everything you need for pre-training. And this here is just the standard ImageNet, I believe, the ImageNet normalization. So these are the means and these are the standard deviations from the ImageNet dataset. And let's already resize our image actually to this 800. And I believe if you rescale the 640 to 800, you get 600 here. Right, fairly sure. Okay, and then let's display it just because we can. Okay, it's a bit squished, but we don't care. And let's put that up here, so we only need to execute it once. Nice. Okay, so from now on, it should be a breeze. So what these transforms do is they resize the image. Okay, we don't need that anymore. They make it into a tensor, and then they normalize by that. So if we run our image through this, because our image right now is this pill image, right? So our image is this pill image, but if we run it through the transforms, then we'll get a tensor. So that's pretty cool. So the model, as it is a deep learning model, it expects batches. So we'll unsqueeze that in the first dimension, and then we get batches. So shape, let's see, we don't have unsqueeze. No, of course we don't. So this is one image of 3 channels of 600 by 800. So this is the y and x coordinates, I guess, are shifted. Yes, in PyTorch. Cool. So we'll call this our image tensor. Now we just need to put it into the model. So model, we put that in there. And since we don't, let's actually up here put the model in eval mode. I don't know if that's already done, but you know, you can never be sure enough that the batch norms aren't. So I think it probably doesn't have batch norms. Okay, you're not utilizing the GPU. We'll do that. We'll do that. Thanks. So how do we use the GPU? We put our model on the GPU. Model equals model.cuda. Yes? 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 I think so. This is gonna work. Okay. We're gonna come back to this later. So we forward our image. Of course, we also need that on the GPU. And this worked. Did this work? This worked. Nice. Okay. And since this is just for evaluation, we should probably go with no grad right here, because we don't need this whole gradient stuff if we do that. Okay. I'm dumb. There you go. And nothing happens, of course, because we need to capture the output somehow. Let's look at that. Output. Wow. Wow. Just wow. So the output is a dictionary, right? Because we get back class labels and bounding boxes. So let's look at the pred boxes. Let's look at that tensor. That's a tensor. Very nice. Let's look at its shape. Let's not print giant tensors anymore. Cool. So since this was a batch of 1, we should probably go with the 0th. And you can see right here, there is 100 bounding boxes and each one has 4 numbers. And if you go with the other thing that's in there, the logits, then you'll see that there are also should be 100 logits. And hello, there should be 100 logits, and each one is of size 92 because there are 92 different classes. 92? We'll see about that. Well, one is going to be the nothing class, right? By the way, how many classes do we have? We have 91 classes. Okay. Cool. We can deal with that. All right. So what are we going to do next? What we want to do is for each of the logit predictions, we want to find which class it corresponds to. So what we're going to do is we're going to take the argmax of the last dimension, right? So you can see here almost all of these things correspond to class 91, and class 91 is not in our classes because our class is only length 91. So that must be the nothing class. Right? So what we can technically do is for logits and boxes in, let's just zip them together. And like this. Okay. Class is the logits argmax. If that's 92, or let's just say if that's larger than the length of our classes, we'll just skip it for now. Okay. So that should work somehow. And if not, then our label should be the class index right here. So let's just see what the detector detects right here. It detects nothing. Why does it detect nothing? That doesn't seem good. What are we doing wrong? We zip together the logits. Oh, yeah, of course. We still need the 0th entry. We are dumb. Da-dum, da-dum. Cool. So. We can delete this. And now, finally. Beautiful. Dogs. 2 dogs detected. Excellent. So now for each of these dogs, we want the bounding box, okay? So now we somehow need to think of how are we going to draw this on an image. And well, let's actually make a copy of that image because I don't really trust myself. And then at the end of this, we're just going to display that image, right? Now, actually, the reason I make a copy is because in this pillow library, you can actually draw on these images, and we're going to use that to draw these bounding boxes. So for that, we need an image draw, if I remember correctly. And I think later we also want some text, so we need an image font. Yes. All right. So let's draw a bounding box right here where, so first of all, let's look at that bounding box. Let's call this box, print box.shape, and break right here. What's happening? Let's not do this right now. So this is a boxes of size 4. Now this could be 2 things. It could be x0, y0, x1, y1, so the 2 corner points or the kind of the boundaries, or it could be x, y, width, height. Now from the paper, I know that they predict the center and the width and the height. So I'm going to go with that. And I'm just going to guess that it's like x, y, w, h, and not some other way around. If this is a bad guess, then yeah, we'll see. We can just print out one of these boxes, and I honestly have no clue. That looks reasonable. Oh, by the way, we should scale that up. Yeah, so these are normalized coordinates, probably between 0 and 1, so we should scale that up. So we should probably the x coordinates, we should scale by 800 and the y by 600. So let's do it. So first of all, we scale our box by 800 in the x, and here's a y, and the width is the X direction, and this is the Y direction. Boom. Okay. We should probably get that on CPU. We'll just hack together a bunch of things right here. Okay, so now this isn't the correct, so our X and Y and W and H are going to be this box. So now we need to actually draw on the image. How are we going to do that? So let's first go x0, x1 is x minus w half, x plus w half. y0, y1 is the same for y with h plus h half. Coolio. Now we need an image draw object. So I think draw on this image. So whatever you draw on the draw object will end up on the image. So we can use that to draw a bounding box. And let's just quickly look it up. So pil python draw rectangle, maybe? There we go. Okay, so there's this rectangle. Yeah, there's the rectangle function. And you can see you put in a shape XY here and width height like this. Wait, for real? We wouldn't even need to transform it. I'm pretty sure you can go X. I thought I remember you could do the different thing as well, but it's called rectangle. Okay, so let's do that. So draw rectangle, and we'll go x0, or we'll go x, y, width, height. Let's display that down here. Yeah, that looks nothing like we want, but it's, you know, it's a start. Maybe actually we need the other thing here. We need x0, y0, x1, y1. Yes, yes, doggy. Okay, we still have the break in here. Now we get both dogs. Nice. Nice. Okay. Let's do, I think, fill. Yes. Red. And let's go for width 5 or so. 5 seems like a good width. Oh god, 5 is a terrible width. Oh, it's not fill. I think it's outline. Yeah. Okay. Let's still go with 5. Cool. We got our dogs. Now we need to put like some snappy text labels. I think there's actually a pil image draw text. I think that exists because I've this font thing. Yeah, exactly. So you need the font thing. Get a font in there. And then, yeah, exactly. You could put a text like this. Okay, so you probably need the X and Y coordinates of the text. So let's do that. W.text, and let's just go with X and Y right here. Put it right in the middle. And the text is going to be our label, of course. And we want the fill, that's now going to be the color of the text. Let's go with white, and the font, we're going to load some font right here. Font dot, how are we doing this? True type. Okay. No cheating. Let's just go with regular fonts. It won't look as fancy, but we'll be fine. So, where is our text? You see it? I don't see it. Red. Let's make it red. Yes, there we go. Okay, so it wasn't red enough. This should work when it's white. Did I just not see it? I'm dumb enough. Cool, so we have 2 dogs. How easy was that? Actually, we wasted the most time with like bounding boxes and stuff. Absolutely cool. Right? Okay, so now we can have some fun with it. I'm going to scale this down for a bit because you don't need to see the actual code anymore so much, so you can see the image more. So we'll go to the images, and the first thing I want to do is the dress. What does this think of the dress? Okay, so we'll copy that and we'll go into our collab and just paste this right here. Bada boom, bada boom. Sounds nice. And what is wrong? The size of a tensor must match the size of a tensor. We do something wrong. Transform image. Our image is this. Maybe this is like an RGBA image. I think if this is RGBA, we should just convert it to like an RGB. Pretty sure you can do something like this right here. This should work. If it has an alpha channel, then that will remove it. Yes, now it works. Okay, let's see what the model thinks of this. There, okay, apparently there's a car, and there's a surfboard, and there's a person, and there's a person. Nice, see? Well, we didn't figure out whether the dress was blue or white or gold. It was just a person. Now, you could actually like threshold by how sure you are of a given class, but where's the fun in that? So let's go further. Let's do some Rorschach Ink Blots, because those are always lots and lots of fun. So, which one should we go for? This one looks like fun. Okay. So we'll put this into here. And it's astonishing, right? This Coco data set, it only has these 90 classes. It's like it doesn't have anything else. So it's a cake. It's a cake. And this here, what is it? Okay, we'll have to go maybe with blue. What is it? Stop sign. Okay, but so you might think, what if we want more? Like, what if we want more predictions? So there is a hack, right? Right now, the model can always assign mass to this not a class thing, like right here, this class 91, in order for it to say, I don't think there's anything there. But generally, we have 100 predictions, right? So you see where this is going. So yes, let's change it a bit. Let's change it up a bit, and let's go here. Let's first extract these tensors and boxes. Okay, so we have the boxes and this and logits and boxes. Okay. So we got that. What we want to do is basically we want to filter the, we want to basically just remove the last class before we do the argmax. And thereby we want to force the model to make a prediction. Now, it won't be a very good prediction because, of course, this is only the second highest class and it's arguable how much that counts. But still, it'll do something. So this must be done in the logits, right? So we'll look at the logits, and the logits are of shape 100. So we have 100 predictions of 92 classes. Now, the first thing we want to do is just remove the last class. So let's go everything here until the last class. All right, so now we have 91. Actually, let's make it more generic. Whatever's in however many classes there are. Okay, so we don't have this class anymore. So now if we do the softmax over the last thing, we can technically, we get 91, but now they're normalized. So they add up to 1. So it's kind of a probability distribution. Next, we want to find the max over this, and that will give us a max output. So we don't want to plot all the 100 predictions, because that would just be like squares all over the place and we'd have no clue what's happening. So this max output right here, what we're trying to find is let's say the 5 best predictions or so, the 5 ones where the model is most confident. It's not really a good metric, but you know. So these are the probability values of all of the 100 predictions. So what we want is like the top K. Okay, so let's go with 5. And again, we'll get like a top K output. Let's call that top K. And I think it also has like values and indices. Yes. So now we simply need to filter from the logits and the boxes where these top ones are. So we'll filter the logits. We'll filter the logits by that, top K indices, and we'll also filter the I am not very gifted today. Boxes. By the way, I'm using a collab just because it's nice to kind of play around with a model, because if I were to use a file, I'd have to restart and reload the model over and over again. Just not as nice, right? So now we have the logits and the boxes, and if we do that right now, we get always the top 5 predictions. How nice is that? And you can see the top 5 predictions are probably still KKKKKKK. Just to verify that, and we can put its shape. Blah. See, this is what I don't like about this stuff. Yes, okay, so we just have 5 predictions of 92 things. And we don't want the 92, we've already said. So we just want the 91. Let's actually put that here. Okay. So now we have 5 by 91, and now it should give us the top 5. Ah, there we go. So many cakes and many stop signs. That's fine. That's cool. So the ultimate test right here is going to be, yes, the human adversarial example. Let's check it out. So we'll put in a Jackson Pollock image, and we'll see what the model says. Now we're actually forcing it to make predictions, right? So it can't escape. It will need to do something. Okay, I made another mistake. I would need to copy the image address right here. Like this. That's what happens when you're not an idiot. You get the actual image. So what does the model think of our pretty image? Okay, I can't even read that. So let's make this into white. Bird, bird. Okay, lots of birds in this image. Clearly lots of birds in this image. Let's try another one. Let's go with this one. Yes, absolutely. Love it. Okay, so we copy image address. Bang, beam, boom. More birds. Wow, there's a lot of birds in these Pollock images. Just so many birds. Okay, let's try one last. How about this one? This one is a bit more human friendly, right? Put it in here. Bang. And okay, we get some detections. There's a clock right here. There is a, what's that? House? Horses? Let's print the labels. So just so we know what they are. Cake, horse, car, horse, and clock. Okay, so I see the clock, like this here is clearly a clock. Then this rectangle on the right side must be something. Let's put this to red as well. Now that's terrible. White, back to white. How about back to white? Okay, clock. We got horse right here and house probably. And the entire image is again a cake. Yes, okay. So as you can see, it is a pretty good system, but of course it is only these 90 classes. But it's for now it's pretty cool and it works pretty well, and just the easiness with which you which you can get this stuff. Elephants in Kruger National Park. Just the easiness is astonishing. You can just load it up, kind of have a bit of a notebook, and with a bit of like a very few lines of code, you can put something together that detects these bounding boxes. Lots of elephants, and remember we only have the top 5 elephants right here. So what happens if we go for more? Where is our top K? So here we can maybe say the top 15 predictions. And as always, if we want to make the model to make its own decision, we can simply revert back and add back the no class label. All right, with that, I hope you liked this video. If you did, then maybe tell YouTube that you liked it, share it out, and I will share this notebook in the description for you to find and play around with. All right, thanks for watching. Bye-bye.